Hello everyone, I'm Yuhao Wu. I'm from Shenzhen University. The title of the presentation is Pairwise Intent Graph Embedding Learning for Context-Aware Recommendation. This is a joint work between the Guangdong Laboratory of Artificial Intelligence and the Digital Economy, Shenzhen University, and Huawei 2012 Lab. So let's get started. Previous studies have shown that contextual information often influences users' behaviors. Then, context-aware recommender systems are proposed to provide more fine-grained recommendations, and the key to performance of context-aware recommendation system is the learning of the contextual features. By observing the information related to contextual features, for example, the top row is the number of contexts each user has. The middle row is the number of contexts each item has. And the bottom row is the frequency of each context. We can observe two specific sparsity problems in context-aware recommender systems: interaction sparsity and feature sparsity. How to effectively solve these two sparsity problems is an important challenge for context-aware recommender systems. On the other hand, knowledge graphs have been proven to effectively relative the data sparsity as an actual information source. Therefore, an intuitive idea is to introduce a knowledge graph into context-aware recommender systems. However, a key difference is that these sparsity challenges in context-aware recommendation systems are closely related to the contextual features. How to use knowledge graphs to enhance the contextual information its relationship with other information is an open problem. So this drives our goals in this work. Design a new graph structure with knowledge graph for context-aware recommender system, pairwise intent graph, or PIG. Design a pairwise intent graph embedding learning, or PIN, to obtain refined embeddings of all the features. Finally, the refined embeddings are used for the embedding layer of the downstream recommendation model. We first list the required notations, including users, items, contexts, instances, and the knowledge graph associated with the items. We refer to FM as the base model in this work, and it can be divided into three stages: initial embedding, feature interaction, and model training. Recall that our goal is to obtain a better embedding P using the PROC framework to replace the original embedding E. This only modifies the initial embedding stage and can be interacted with any recommender system. Intuitively, all interactions of a user in context-aware recommender system can be organized into a personal graph, and the personal graph and KG can be combined by conjecturing the mapping between items and the entities of KG. An example is shown on the left. We can find that it is very difficult to apply directly this graph structure in context-aware recommender system due to the many heterogeneous nodes and the weak connection between the entities and the user and the contextual information. To address the above problems, we propose user intent fusion model to capture the fine-grained relation subintent and the contextual subintent in each instance and generate corresponding intent nodes. This means we summarize different intent information for numerous heterogeneous nodes and use enhanced intent node to bring the relationship between various information in knowledge graph and the context-aware recommender system closer. First, for relational subintent, we define a set of shared intention composed of different relation set of knowledge graph and further obtain a personalized relationship intentions through the user information as shown in equation 2 and equation 3. Second, The context subintent, we combine user information and contextual information in each instance to obtain a user's attention weight for different contexts. Since a user behavior may also be influenced by the preceding behaviors rather than the context alone, we also consider the user's last interacted item as the special context. Finally, we fuse the two subintentions and introduce them as an enhanced node. An example is shown in the figure. After the above operations, we can get the pairwise intent graph as shown in the figure. Next, we introduced how to carry out the effective information propagated based on this graph structure. For the user, as shown in the left figure, we can use the enhanced intent nodes as a hub to propagate information about the items and contextual features. For the item, as shown in the middle figure, we can enhance the intent nodes as a hub to propagate the information about the user, context, and entities. For the context, the information is the first propagated to a contextual subintent node, and the different contextual features will distribute the information according to the attention distribution. Note that we need to feed the information back to the intent node to get the embedding of the intent node at the layer h+1. For the entity, the information propagation only involves the items and relations. Finally, we can obtain a set of refined embedding P, including the user embeddings, item embeddings, and the context embeddings. This is an overall training pipeline for PIN. We can see the graph construction step, pairwise intent join the graph convolution step, and the final recommendation step. This is the complexity of our PIN on online inference and model training. In the experimental part, we choose the three public datasets to evaluate our method: Amazon Book, YEP 2018, and Last.fm. And we also chose a set of competitive methods as the baselines. The specific method is shown in the slides. Here are the implementation details of the baselines and our method. This is the main result, and our method can be found that we can have the best results on the three datasets. Here are some other observations. In the ablation study, we find that removing all subintentions is the most damaging, and the relation subintention outweighs the contextual subintentions. In the parameter-sensitive analysis, first, we can see the number of layers is 2. Our PIN can achieve the best results. Secondly, when the regularization weight takes a moderate value, our PIN can also achieve the better result. Finally, we can find that the expect for a large value. The performance of our PIN gradually improves as a number of shared intent increases. For ease to understand, we show some training example of our PIN. We can find it successfully captured relational subintentions and contextual subintentions of different users in different instances. Next, we group users, items, and context according to their level of association with contextual information and report the corresponding results of different methods. We can find that our PIN can solve the two specific sparsity problems more effectively. Finally, we combine different downstream recommendation models, MF, FM, and MLP. Our PIN can always maintain the best result. And finally, we give a brief summary of this work on this stage. If you have any question, please feel free to contact us. Thank you for your attention.
Thank you. Okay, Do you have any question? Okay.
Oh, thank you. I'm very interested in the work that you have published. P is a very fancy method. As you just introduced, it integrates knowledge graph technology very well and have good performance on different data side. I'm curious, which part of the method do you think has the greatest performance on your model? Could you introduce it?
Yeah, and thank you for your question. I think the reason why our PIN can achieve the best result on the 3 datasets and our PIN can combine the user intent, include the relational intent and contextual intent. And we combine these two sub-intent to enhance the user intent in our graph.
Okay. You just mentioned the intention. Here's my second question. What is the specific meaning of the relationship intention you just introduced? I'm very curious about it.
Okay, let me turn to the slides. In this framework, we can see the relation intent. And in our method, relational intent we extract from the knowledge graph. We can obtain the relation intent through the knowledge graphs composed of the items and entities. And this relation is from the knowledge graph, and we can combine the relational subintent and contextual subintent in the user intent, and we can obtain the more comprehensive user intent to enhance the performance in our downstream recommendation stage. And our relational subintent is more important to the graph, and we can see a interest case. In case study, we can see in the right dataset, YEP 2018, and we can see one user in this graph, in this figure, and the top side is the context of the user, and the bottom side is the relation of the user. And we can see the C1 context is get a highest score. We can think the user is more concerned the city context. And in the bottom side, we can see the P3 is get a more score, and we can say we can assume this user will more concern the restaurant table survey and the star. And in this two-side information to enhance the user intent, I think we can greatly to obtain the user performance in our recommendation system. That's our answer.
Okay, thank you. I got it.
Okay, since we have a bunch of time, I would like to ask you a couple of questions.
Sure.
Let's start with the first one. In the ablation study, you have shown in slide 31, if I'm not wrong, that adding a third layer.
Yeah.
Yeah. The H layer. It implies a significant worsening of the performance.
Yes.
Okay. Do you have any insights of why this is happening? Go to slide 31.
Which slide?
31. 3 slides before. Okay, here. You can see that when we use the number of layers equal to 3, so is that the meaning of being 3? Yeah?
Yeah.
We have that the recall falls down from 0.30 to 0.2. Okay?
Yeah.
It's a big drop. Okay.
Thank you for your question. And the layer of the graph in the experiment, we find the layer set 2 can obtain the more effective information of the user's intent and knowledge graph. And when we set the layer on 3, we find that the result on our performance and maybe because the overfit in the graph learning, we find the 2 is the best answer on our graph learning.
Okay, thank you for the explanatory answer. And the other question is related to the overall performance table that you had.
Okay.
Yeah, no, that one I think. No, not the architecture, the performance table. Yeah, this one. So this was very, very interesting when I read your paper, because we have 2 different methods that are user event graph embedding, so UEG, and ping, that are achieving a very astonishing value in terms of performance. So they almost double all the other methods. Okay. Do you have any insights for that? Any reason why exactly these 2 models are working so well? Because that could be, let's say, an intuition that the community could use.
Yeah, I think our merger the 2 modules to enhance the user intent obtain, and we base the user event graph, and to combine the knowledge graph and the relational intent into our method, and our method can achieve the best performance. And I think the most important is the knowledge graph's relationship between the 3 data sets. And the 3 data sets, the knowledge graph is very important to our user intent. And the relational intent and the contextual intent all enhance the performance in our method.
Okay,
Okay,
thank you.
Thank you very much.
Let's thank the presenter again.